In this video, we'll give an outline of sufficient assumptions for consistency and asymptotic normality of the generalized method of moments estimator. First, recall that the Gmm estimator, where we have over-identification, so r is greater than k, is given by theta hat Gmm, and it's a function of the weight matrix Wt, and the estimator is simply given by the arc mean with respect to theta of the quadratic form Qt of theta. The quadratic form Qt as a function of the parameters is given by the sample moments transpose multiplied by the weight matrix multiplied by the sample moments. And here the sample moments are equal to 1 over t, the sum from t equal 1 to capital T of the function f of the model variables Wt, the instrument set t, and the parameters theta. To sketch the asymptotic properties of the Gmm estimator, the first thing we do is a Taylor expansion of the sample moments, gt of theta, around the sample moments evaluated in the true parameters. That gives that the sample moments are approximately equal to gt of theta 0, so that's the sample moments evaluated in the true parameters, plus dt times the difference between theta and the true parameters, and here we have that dt is the derivative of the sample moments with respect to theta prime. So look at the dimensions. Recall that we have an r by 1 vector of moments. Here we have an r by 1 vector, and we are differentiating with respect to theta prime. So that is a 1 by k. That means that dt has dimension r times k. So we have here r times k, and the distance here is k by 1 because theta is a k-dimensional vector. In box 1 in lecture note 8, we show that we can use the Taylor expansion to derive an expression for the Gmm estimator that is approximately equal to the true parameters plus a sampling error given by dt prime vt dt inverse dt prime wt, the sample moments evaluated in the true parameters. The dimensions, this is a k by 1 vector, k by 1, dt prime is k by r, r by r, r by k, k by r, r by r, and finally r by 1. So this defines a k by 1 vector, and note that we can think of this as defining the estimates approximately equal to the true parameters. So that's our theta 0 plus a sampling error. And the sampling error depends on this term here. That is the sample moments evaluated in true parameters. Next, we state 3 sufficient assumptions. The first, which I'm going to call assumption 0, is that the moment conditions are correct and that we have identification, which means that the function g of theta 0, so that's our population moment condition, equal to the expected value of f of the model variables instruments and the true parameters is equal to 0. The second assumption is an assumption about the data. Specifically, we assume that the data is such that a law of large numbers applies to the function f of wt set t theta. So that says that the sample moments gt of theta, which is equal to 1 over t, the sum from t equal 1 to capital T of f wt set t theta, is going to converge in probability to the expected value of f of w set t theta. Third, we assume assumption number 2, which states that the data is such that a central limit theorem applies to f of wt set t theta. This says that the square root of t multiplied by gt theta, which is equal to the square root of t divided by t, the sum from t equal 1 to t of f wt set t theta, is going to converge in distribution to a normal distribution with a mean of 0 and an asymptotic variance S. Note that here we have formulated the assumptions directly as an assumption about the function f, and these assumptions can be translated into precise requirements for the data. Note, however, that weak stationarity and weak dependence of the data Wt, that's the model variables, and the instrument Zt, that implies assumption 1 and 2. So instead of assumption 1 and 2, we could simply state that we assume the data to be weakly stationary and weakly dependent. We now look at the first result, that is that assumption 0 plus 1 implies consistency of the Gmm estimator for any positive, definite, and symmetric weight matrix Wt. To understand the intuition behind the result, we look at the box that we have up here, and in particular we look at the last term, the sample moment evaluated in the true parameters theta 0. Assumption 1 implies that the last part, this part up here, the sample moment evaluated in true parameter, that is going to converge under assumption 1 in probability to the expected value of f Wt Zt theta 0. So that's the first part, and this is equal to the population moment evaluated in true parameters. Now we need assumption 0, because assumption 0 says that the population moments are correct, so g of theta 0 is equal to 0, so that means that the last part out here is going to be equal to 0. If you now look at the expression up here, the gray expression, note that the last part, this one, if that is going to converge in probability to 0, we have a consistent estimator. So jointly, assumption 0 plus assumption 1 implies that gt of theta 0 converge in probability to the population moment, which is equal to 0, such that the estimator, the Gmm estimator, converges in probability to the true parameter for the sample size going to infinity. The second asymptotic result is that assumptions 0 plus 1 plus 2 implies asymptotic normality of the Gmm estimator. So the expression up here in the gray, we can rewrite a little bit. So we can rewrite it as the difference between the estimates and the true parameters. That is approximately equal to dt prime vt, dt inverse, dt prime vt, and then we have the sample moments evaluated in the true parameters here, and then I'm just going to normalize by the square root of t here, and I'm going to put the square root of t in here. Now under assumptions 0 plus 1 plus 2, it holds that this expression out here is going to converge in distribution to a normal distribution with a mean of 0 and an asymptotic variance of s. And this expression out here is going to converge in probability to d prime v, d inverse d prime v, where v is the probability limit of Wt for t going to infinity, and d is equal to the expected derivative of the function f with respect to the parameters theta prime. So we can combine the results. The square root t multiplied by the estimator minus the true parameters is going to converge in distribution to a normal distribution with a mean of 0 and an asymptotic variance v. V is given by d prime v, d inverse d prime v, and then we get the s v prime d, d prime v, d inverse estimator. That's all for now. Thanks for watching.